Hey everybody, so for today this is going to be sort of a pre-recorded lecture, so if you're watching this exactly at Tuesday at 1 p.m. I'll be at the Faculty Senate meeting um, getting involved in various discussions over there. So for this lecture, I'm going to try to emulate like an hour or so long lecture as I would during a regular class. So I'm going to continue off of the last week's content. So we basically talked about quicksort and the proof of quicksort. So basically we know quicksort does work and it's going to sort the array of n elements. So you want to know, well, what's the runtime for quicksort? So runtime for quicksort. So in CS302, you probably already have seen basically the analysis of quicksort. So essentially, quicksort, well, the runtime depends pretty much on the pivot chosen. So the run time So either way, when you are doing quicksort, what's going to happen is you're going to pick a pivot and you're going to partition the list in two pieces and call quicksort on both sides. So whether or not the pivot is a good or bad pivot, it's going to work, but a bad pivot will result in a worse case or a bad runtime, and a better pivot will result in a better runtime. So either way, we are going to go into the worst case analysis, but you want to know, well, if a good pivot is chosen, what's the most number of steps it will take, and if a bad pivot is chosen, then what's the most number of steps it will take. So we're going to go over this big O, big theta type thing. So basically, if the pivot chosen is the median of the list. So basically, that is sort of our goal whenever we do, in fact, sort of implement quicksort. We want to have the pivot chosen that's the median of the list. So if that happens, then of course the partition, the I and j counters as they're moving across the list, they will actually meet in the middle, because that way exactly or roughly half of the elements will be smaller than the pivot and the other half of the elements will be larger than the pivot, so it will break the list in half. So what will happen there is the runtime we achieve in this situation is going to be, well, that's given the following current relation. So when we go ahead and look at this t of n will be sort of the time for quicksort. It'll actually be 2 t of n over 2 plus theta n. Of course, I'll just be consistent here and say t of 1 equals 1. So a one size list, of course, will be sorted. So this recurrence relation, the theta n part, is that partitioning work you're doing. And we already sort of explained last time that partition does in fact take theta n, or a linear amount of time, to perform that. And if the pivot chosen is the median, then what's going to happen is it will break the list into two pieces of n over 2 apiece. Each piece will be n over 2 in size, and exactly two of them. So this is going to be the recurrence, and we know this is the same recurrence relation as merge sort. So we know that the runtime for quicksort will be theta n log n. So of course, I could do a more visual sort of proof for this, but this recurrence relation really does paint the picture. It shows exactly how the algorithm will run if the median is always chosen. Now, we don't always have to choose the median every single time. So for example, like I did an example in class, what if we pick a median where, let's say, it breaks the list into 1/3 of the list on one side and 2/3 of the list on the other side. If we have that, then the following recurrence relation is going to follow. We have t of n over 3 plus t of 2n over 3. And of course, as always, the partitioning, oops, I'm kind of in the way, so let me just move this down. The partitioning phase always takes theta n no matter which pivot is chosen. So here we break the list into two pieces. One will be in size 1/3 of the list, and the other piece will be 2/3 of the list. And if you use that tree method, which I went over when we did recurrence relations, this also works out to be theta. Oops, I should have also put the base case as well over here. So of course, this also works out to be theta of n, t of n equals theta n log n. Now, if you break the list not quite evenly, it's still going to be theta n log n. It'll be a constant factor times worse than if you break it in the middle, but it's still going to be asymptotically n log n. And in fact, if we do break the list into two pieces where they're both fractions of n, as long as the denominator you're breaking it by is a constant much less than n, then in fact it will be theta n log n. Now, depending on how big each piece is, it could end up being a constant factor times worse than the perfect case where it breaks in half, but it'll still be some constant multiplied by n log n, which will still be, of course, n log n. So as long as we break it into the two fractions, so we have these two pieces that are both fractions of n, that's going to make the runtime pretty good. So now the worst case scenario for quicksort, so this was, hopefully I think I'll outline this. So if pivot shows a median, or I can also write this here, if it's a fraction, it breaks this into a fraction of two pieces, then it'll be n log n as well. Now, in the worst case for quicksort, is if we, so what worst case is when we sort of break the list into, again, two pieces where one piece contains a constant amount of elements, and the other piece contains n minus c. So c was the constant for that first piece. Other piece will be n minus c amount of elements. So this is really the worst case, where the one of the pieces that's broken into is not a fraction of n, but is just some small constant, like c, for example. So if this happens, we have a very bad case for quicksort. So the recurrence relation in this particular scenario is the following. We have t of n equals t n minus c plus theta of n. And then t of 1 equals 1. So if we have t of n minus 1 plus theta of n, or n minus 2, n minus 3, or whatever value, it's very easy to show that is going to in fact be sort of quadratic in this case. So we can use our methods of the antiderivative method to actually work this one out. So it's just for the sake of this, let's do that. So t of n minus t n minus c equals, I'll just choose n. So we have theta of n, which means we just pick any linear growth rate. So I'll just pick n, although I could even pick c times n even if I wanted to, but I'll just choose n though. And then we divide both by c. So c is a constant, so what happens here is t prime of n will be n over some constant. Therefore, well, I guess I'll say it then. Therefore, t of n will be theta of n squared. I'm not going to try to work the calculus out on this since I don't remember integrals. It's been a very long time since I've done calculus. Yeah, I guess maybe since like '05. So it's been a while for me. So I'm going to not try to attempt this, but we can all agree on the fact that this is going to, antiderivative will be some quadratic type of function. So as long as c is some constant, not a factor of n, then this is going to be theta of n squared. So now we have these two particular instances for quicksort. We have this n log n instance and this theta of n squared instance. So what's the runtime for quicksort? Now we have to, of course, always assume the worst case scenario. We can't ever assume anything works out nicely. You have to always assume the worst case happens, where the pivot chosen will be really bad, which will cause n squared. But the one issue with quicksort is that having the pivot always chosen that's going to be the worst is not really, it doesn't really happen too often. So really, in a sense, we can almost treat quicksort on average, it's n log n. So for the most part with algorithms, we always have a case where the worst case and the average case are not really so much different from each other. They're relatively about the same asymptotic growth rate, maybe a constant factor off if it's average or the worst. So between average to the worst, they're constant off, but they're both asymptotically about the same. But here's a case with quicksort that we can almost treat it really as, and on average, it's really n log n, because most of the time the worst case doesn't really happen. But in the worst case, where you do pick a very bad pivot, it will be theta of n squared. So because of that, we have to say, well, quicksort is n squared, or O of n squared, or theta of n squared, because we have to just always assume the worst case happens, because the worst case encapsulates every single possible scenario. But anyway, the reason why quicksort is really regarded, really in a sense, kind of unofficially as n log n, because of what I said before, it's easy to avoid that worst case because we can also get sort of lucky, and or we can get sort of average, not pick the worst pivot. However, there's actually a way we can sort of guarantee that quicksort will in fact run in n log n time. So let's go ahead and just think of, well, how do we actually make this run n log n time? So the idea is we want to always choose the pivot, choose the, I guess the median value, sorry, the median element as the pivot. Now, of course, it doesn't have to be the median, but I guess if it is the median, then we really have a very good scenario. So now how do we actually achieve this? Now, of course, what if we just sort the array and then pick the middle element? If we do that, well, of course, there's a lot that's wrong with that statement I just made. Okay, let's sort the array first. But if you sort the array, it's already sorted, so there's no point even doing quicksort at that point. And second of all, sorting can be a pretty expensive operation. So we'll go ahead and sort of, maybe show like a proof about sort of sorting in general, but sorting the array first is a bad idea. So the idea is we want to pick the pivot, or sorry, we want to find the median, in O of n time. Now, I didn't say theta because if we can find it faster in n time, that's also okay. So when we're doing quicksort, inside of every quicksort function call, we do a partition step. Partition takes theta of n time. So as long as we can find median in n time or less, then we're okay, because no matter what we do, we have to run this partition, which takes n time. So we don't want to find a median in more time than linear, or asymptotically more than linear. That's sort of the idea. So now what we have to do is, well, we have to figure out a way we can actually find the median O of n time. Now, basically, of course, we can sort the array to find median, but there's actually a way to use partition such that we can find the median, and we don't really have to have the whole array sorted to find the medians. That's kind of the key. So we have to use a partition sort of functionality to allow us to find the median quickly. Let's go ahead and just make sure I have my notes not sort of let notes in order here. So we're going to go over the selection problem as to find the median. So let's look at the selection problem. So selection will be a function call, I guess. It will take in an array, a k value, and then L and R. So L and R are going to be the leftmost index and rightmost index of the array we're trying to look at. So initially, L would be 0 and R would be n minus 1, the whole entire array. We pass in the same array all the time in K. Well, K is going to be the element we're trying to find. So selection in this case, so selection will find the kth largest element in the array. So if we're looking for the median, then it's set k to be n over 2, or if it's the even or odd element list, and it's a little confusing, but for now we'll assume that we pass in n over 2. That's the rank we're trying to find. n over second element would be the median. So selection problem finds the kth biggest element of the list. It's not going to have to sort the entire list, because it turns out we won't need to sort the whole list to know if it's the median. So for example, we can think of it like this selection problem. If, let's say, I pick a pivot in my array and I run partition with that pivot, and let's say after I partition, I swap the pivot with index j, and the pivot is going to be in its correct position. Let's say we have a 25 element list. So I believe the 13th element would be the median. Let's suppose that we pick some element and we run partition, and it's going to be in its correct final position after partition, and there's 12 elements to the left of this element. So this is a 13th ranked element, which means it has to be the median. And we don't have to sort the whole list to know that, because when we do a partition, after we have the I and j cross, the pivot goes into index j, and that value will never ever move. It's going to stay in that spot from that point on. So if that happens to be the kth biggest element, we're done. We found the kth largest element. That's what selection actually does. Let's go ahead and go over the details of how to have selection work relatively quick. So the details of the algorithm. So what's going to happen is we have to break the array into n over 5 pieces where each piece contains 5 elements. So the key here is 5. That's like the magic number for this algorithm. So you first want to break into these 5 pieces, and then what we're going to do, I'll zoom out so you can see the whole entire code at the end. But anyway, we break this into 5 n over 5 pieces, and we find, so we're going to sort each piece to find the median of that piece. So each piece contains 5 elements. So we can do insertion sort on each individual piece. That will take constant time to do that because we have 5 elements. So to sort 5 elements, we can do it in constant time using any sorting algorithm. So the simplest one really is just to use insertion sort or bubble sort. What doesn't really matter. They're going to both be constant. So okay, fine, bubble sort we can use to sort each one and then get the median very quickly. And there's n over 5 pieces. So let me go ahead and write some more math here. So each. So it takes. So it's going to take, basically, it takes O of 1 time, and we have n over 5 pieces. So this entire process takes, I guess we'll just say, theta of n time. So to find so these n over 5 medians will take theta of n time, because each piece has 5 elements. That's constant time to find the median of that small piece, and it's n over 5 of them, so it will take theta of n over 5, which is theta of n. So in theta of n time, we can break the list into these size 5 chunks, and then find the median of each one of them, theta n time. So it's not bad. So we want to make sure we don't go beyond theta of n on any of the steps here. So now what happens is we want to find the median of the n over 5 medians. Now, in this situation, suppose that, well, n over 5 is a very big value. If that's the case, well, we're going to have a new list of size n over 5, and we're going to have to call the selection algorithm recursively on this n over 5 size list. So what we can first do, so if n over 5 is large, we pass the list of n over 5 medians into the selection algorithm, into the selection function. So we pass in a new array, and this array will be the list of these n over 5 of all these medians, so there's n over 5 of them. If it's a very big value, we're going to pass that into selection. So we're going to do it recursively, and then of course, by the magic of recursion, it's going to return back the median of these n over 5. Now, of course, if let's say we have a very small constant number of medians, then in constant time we can find the median of the medians. So then, of course, if n over 5 is, I guess, a constant, then we can find the median of these medians in constant time. So I'll just say O of 1 or theta of 1 time. So the idea is, one way or the other, we're going to get the median of those medians. So that's going to be our end result. One way or the other, we're going to get that. So now we're going to choose this median of medians as the pivot for partitioning. So we do the exact same partitioning loop, just like with quicksort. So nothing different there. So far, all the steps so far is not anything too drastic. The only part is, if you have to recursively call selection on each part, then it doesn't make the code any more complicated. We just have to do the exact same work on this alternative list of these medians. But I'll do an example of this to give us an idea, but I'll pick a small example. Well, small as in it'll be 25 elements, which is relatively small compared to 10,000, I suppose. But I'll do an example so we can better see how this actually works. But anyway, we do a partition now, and then of course, after partitioning, we are going to find, so after partitioning, the list, we will know the rank of the median of medians, or that sort of pivot we chose, that was the median of medians. So we will know the rank. So at this point, well, we have a few scenarios. We know what the rank is, because once we do a partition, we know after we swap the pivot with index j element, we know that that element is now fixed. So that's where the element is going to go into. If you were to sort this list, that element is not going to change. That's going to be the position where it has to be in that sorted list. So without even sorting the list, we know the rank of that value. Pretty neat. So then, at that point, if the rank or the index of where this element is equals that k value, well, then we're done. Then just return, that pivot value, I guess, if you will. Because that is the k's biggest element. So if k is n over 2, that's the n over second number. Now, of course, it could be a plus or minus 1 if it's even or odd list, but we'll leave that detail out. It's not the main idea for this algorithm. But anyway, that's our first step. Now, of course, well, let's suppose that, so if the rank is less than k, that means this k's biggest element has to be somewhere on the right side of our list. So then we have to call selection and pass in, so in j plus 1 into the L argument. Or in other words, we just simply have to call selection, call selection on the right side of the list. You call it on one side. Not on both sides, just one side, which we can see right there. That might already give us an idea that this is going to be a faster approach to find the median than sorting the entire list, because we don't have to even care about the left side, because the median cannot exist there, because we have too few elements on the left side of that j value. So the right side has to be where the pivot has to be. Where the median has to be. And then else, so I guess the else case, or just another if statement, I suppose. If the rank is larger than k, then call selection and pass j minus 1 into the R argument. And then L remains the same, K remains the same, the array remains the same. In other words, we just simply call selection on the left side. And of course, you're going to return the result. So when I call the selection on the right side, it's going to go through recursion and it's going to return back the median. It will find it eventually. So both these if statement cases return the result of the selection. So I'll put this here in red. Return the result of selection. And same idea over here. Just return what this function returns. And I hope, I keep spelling this wrong. I hope it makes sense. I'll get out of the way here. I hope it makes sense that this is going to definitely work. I mean, we don't have to sort the entire list to really sort of find that kth largest element. So this is going to be the entire pseudocode here. Wow, I wrote a lot of stuff. Wow, that's a lot of stuff. Let me go ahead and underline this so I post the notes. Then you'll do that. So anyway, selection. Yeah, I don't even know how box this in actually. I'll separate it from the part above, I guess. Anyway, so yeah, it's a lot of stuff here. So of course, I'm going to post this up onto Canvas. But of course, you can just kind of look through this. Hopefully my handwriting is readable. I think it's okay. I mean, But anyway, that is a selection algorithm, and that's going to definitely work. So let's go ahead and do an example of this on a list. Now, hopefully it does make sense that this is going to work. You don't have to sort the entire list to really get the k's biggest element. Of course, we're going to pass in n over 2 in for k, of course. So that's how this works. Alrighty, so let's do an example. I have a really big example here, so it'll take a while to write this down. So I guess you could just fast forward the video, I suppose, to not have to watch me write all this out. So I'm going to try to fit this into one frame. So 100, which I'll write this a little more to the left here. 135, 97, 63, 32, 76, 46, 55, 84, 75, 44, 10, 24, 17, 60, 96, 43, 86, 59, 71. I'll have to go on a different line here, unfortunately. So last line will be 73, 70, 74, 52, and 88. So hopefully I wrote this all down correctly. So we want to find the median of this list using our selection algorithm. So the first step is we want to go ahead and break this into n over 5 pieces. So 1, 2, 3, 4, 1, 2, 3, 4, 5. We have this piece, 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And of course last 1, 2, 3, 4, 5. There we go. So we have these chunks. So I'll just box all this in. So the first step is just like I said before, we got to find the median of each of these. Now, of course, 5 is the magic number. So since there's 5 elements, it will take constant time to sort these and find the median. But of course, we're not going to sort these. We can just easily just look at these and find the median of each block. So in that first block, I guess every third element will be our median. So in this case here, first, the smallest one is 32, then 35. So then 63 is going to be our median in this block. So let me make sure I'm correct with my notes. Yes, I am. Then this other block, we're going to have 5 elements. So the third element will be the median. So first is 46, then 55. Then we're going to have 75 as our median. Then in this other block, we have 10, 17, so 24 is our median. Yep. Then in this block, we have 43, 59, then 71. Yep, that's our median right there. And our last block, we have 52, 70, so 73 is our median. So that was pretty easy. Found our median. Now among these, what's the median? Now in this case here, so here's where if let's say we had, in this case n over 5 is going to be exactly 5. So we have 5 medians, so we can find the median of those 5 very quickly. Now in theory, if we had a 10,000 element list, we'd end up getting 2,000 medians, right? We'd have to build a list of size 2,000 of all these medians and recursively call that into or pass that into the selection function, and it would return back the median of those, and we could go ahead and continue on this. But luckily here we have only 5 medians, so we can very quickly find this. So what's going to be the median of these? Well, 24, 63. So 71 is going to be the median. So I'll go ahead now use blue to box this in once more. So this will be the median of medians, will be 71. That is the case, yes. So I'm going to kind of shortcut this a little bit. So what we would do is we would take 71, put it, so if you were to actually run partition yourself, you would put 71 and then the 100, you'd swap those because you want to have, at least the way I was taught how to do partition, is I always put the median to leftmost position in the list, so that way it's out of the way. It's not going to get in the way when I have the i's and the j's moving. So you go ahead and stick 71 to the front, so swap the 100, the first element in this list, with 71 and then run partition. So again, I mean, for like homework or whatnot, that'll be a sort of a very redundant, very sort of boring exercise to do. But I'll go ahead now, sort of, I'm going to sort of skip ahead, and after I partition, here is going to be my result. So this is going to be after partitioning. Just made this video a little shorter, and of course, I mean, it's not hard to do this. It takes a long time, but it wouldn't be hard to do this. So the standard partitioning you've always done when we did quicksort the other day, or we did quicksort for CS302, same partitioning loop, nothing different at all. So now we have the following list after partitioning. Of course, can skip ahead or zoom ahead in the video or skip ahead in the video. And then 71 ends up going over here. 96, 75, 86, 84, 100, 73, 76, 74, 97, and 88. So we broke this list into two pieces, basically. So what I did was I had 71 at the very beginning, so I swapped the 71 with the 100, and had I set it at 35, j at 88, and I would just sort of do that same work, and at some point i's and j's crossed, and I swapped the 71, I guess, looks like at some point j became 60, I guess, and then we swapped the 60 with the leftmost element, which was 71, and 71 goes over there. So this is where 71 would go in this potentially finally sorted list. So we want to find the median. So I'm guessing the 13th element would be the median of a size 25 list. So let's go ahead and count. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that means 71 is the 15th sort of ranked element, and it's not the 13th, which means that we know for sure that somewhere over here is where the median has to be somewhere here. We definitely can conclude that. So unlike sorting the whole array, we don't have to worry about the right side of 71 because the median cannot possibly be there. So we can eliminate all those elements right away and focus only on the left side. So 71's 15 right element, therefore, I'll write this here, therefore the median must be in the left side of the pivot, which in this case 71 was the pivot. So we eliminated many elements, but we're not done quite yet. We have to keep on working on this to be able to finally get our median element, our 13th ranked element. So of course, there's ways you can say, well, if it's 13, can we just do like, 2 steps of selection sort to make this work? Yeah, you could, but let's go ahead and just go with the actual algorithm in this situation. So I'm going to go ahead and now run this selection on this list. So I'm going to copy this list over here. Less to right this time, which is kind of nice. 32, 70, 46, 55, 59, 43, 44, 10, 24, and 17. So now we have a smaller list we're going to be essentially using. So again, we have to break this into 5 pieces because we have to find a median. So again, the same work we do again. We have to break it apart in n over 5 pieces, and then do the same process. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we have these pieces right here. Same idea. So we're going to find the median of each of these. So let's take a look here. So, all right. So right now, in this leftmost block, well, let's go ahead and find a median. So of course, we would write the code that would actually sort this, but we'll just go ahead and sort of eyeball this. The first element is 32, then we have 35, so the third ranked element is 52. That's the median of this portion. And then we have, okay, so in this case we have 43, 46, so 55 is the median. And then for this rightmost position, well, we have 10 and 17. So it's really arbitrary which one we want to pick here. Now typically for when we do a median, and maybe in junior high when you do some statistics, you have to take the average of the two medians to find a median. But I guess we'll just pick an element. So I'm going to choose 17. We could pick 10, but I'm going to pick 17 just because. There's no real reason why I chose 17. I just chose that just because we have an even number of elements there, so it's going to be not quite the median, but median enough, I suppose. So now, out of these 3 lists, we have 3 medians now. So again, we can just in constant time find the median of these 3, and we're going to see here that 52 is the third. That second ranked element out of these 3. So this is going to in fact be our median of the medians. So again, what we're going to do is take 52 and 60, swap them, and then the I index will be at 35, J will be at 17, and we're going to partition the list just like we always partition, just like always. Yes, so now we're going to partition. So let's write the list after we run the partition just to save a little bit of time. I think we all know how partition works. So we're going to have the following list. We're going to have 43, 35, 17, 24, 32, 10, 46, 44, and 52 will end up over here. Then 59, 55, 70, 63, and 60. So I'm guessing at some point, looking at this list over here, looks like right around where 43 was is where J and I crossed, and then 52 would be swapped with that 43 value, and then we have this list over here. So in this case, let's take a look. So what rank is 52 in this list? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 52, I'll write this in blue. Okay, I had blue selected, but I didn't put that there. Yeah, so 52 is the 9th ranked element. So that's not the median, because the median is at 13th position. So therefore, the median must be on the right side. So somewhere here is where the median is going to go. And now here's where we can sort of really shortcut this, because now we have a very small list of size 5. So in this situation, this is the 9th ranked element. So the 13th would be 4 elements over. So I guess, looks like the second to last element in this list is going to have to be our median. So we can actually just sort of now do a special base case where we can just sort of literally sort this list and then pick the 4th out of 5 in this sublist. That's going to give us the 13th element among the entire list. So if we do that, we can definitely see here, so let me just make sure I don't mess this up. I think it's 63 is supposed to be the second to last. Yeah, 63, oops, I had it right there. So then it turns out that this element is the sort of the 4th ranked in this list, which would be 4 elements over from the 9th element, which would make this a 13th ranked among the whole entire list. So 63 is the median of this list. I actually verified this by just sorting it and then just finding the 13th elements. I verified this with my example with an actual sorted list, and it came out to be consistent that if I sorted this list, the 13th highest element was 63. So that was the right answer. So that's how we essentially do this. So really not so complicated, especially if we have a small enough list. It's not too bad. We just sort of break into 5 pieces, find the median of each one of them, and pick the median of those 5 or so medians. And then we just pick that as our pivot, partition the list, and find out what rank that element is in, and then decide whether to run a selection on the left or right half until eventually we have a very small size list, and then we can just in constant time pick out the whichever rank we need to actually pick out in that small list. So that's the selection algorithm. And the nice part about this is we didn't have to sort the entire list because we know partition is going to sort the list, or not sort, it's going to find the correct location. Once the I and j's cross, we know that the pivot, that's the position where pivot has to be. So we know the correct sorted position of that pivot. And that's all we really need to know. We don't have to have the whole list to really know what rank this element has to go to, because partition is a fantastic sort of algorithm that sort of helps us with this. So that's basically how we do the selection problem. So that's basically that. So of course for homework, you'd have a similar example to this. It'll be, a long example of 20 or so elements. It's not hard, it's just a time-consuming, tedious process, but it's fascinating how this works. So now we have to try to understand what is in fact the runtime of this algorithm, and we were hoping that it's going to be linear or better than linear. And of course, here's one part of that proof. If it was worse than theta of n or O of n, then I wouldn't have spent all this time in class, or not class, but in this video that you will probably watch, I'm guessing at some point. We wouldn't be talking about this if it was if this was not, at least linear. But of course, we have to prove it, because without a proof, it's not really a sound statement. It would be nice if you could just make up statements and then just sort of, okay, there's your proof. Then my PhD thesis would have been much easier for me to work on if I could have just sort of done that instead. But unfortunately, that's not how things in math always work. So anyway, let's go over the analysis of the runtime for this algorithm. Okay, so let's go over this. So time complexity analysis. For selection. So let's go ahead and create this sort of this generic example right here. So let's say we have our list and we break it into sort of these n over 5 pieces. So we'll have, I'm going to use these dots to represent, I don't know why is there a dot on the screen over there. I mean, I'm seeing it on this, but anyway, we'll have these dots, which is going to represent elements in these size 5 lists. So it's 3 columns, we need 2 more columns. Okay, perfect. Now, it doesn't have to be exactly 5 columns, but we'll use 5 as a generic way of showing this. It could be arbitrary amount, but we'll just go ahead and just do it like this. So in each of these, we have we sorted each of these blocks. So each of these will be, so each one of these is going to just be those size 5 blocks, and it'll be n over 5 of them. So that's all there is. So we sorted each block, and we have the median of each of these. And let's suppose, let's try a space pen. So this element is going to be the median of medians. That element right there. Okay, so now let's go ahead and sort of do a little bit of logic here. So let's suppose, so we want to go ahead and when we do a complexity analysis for any algorithm, we always want to, of course, do the worst case analysis. So right now, let's say we have that as our median, and we partition the list, let's suppose. So right now, let's go ahead and first figure out which elements definitely have to be larger than that pivot right there circled in that space pen. So red will mean larger. So the elements right here, these elements are guaranteed to be larger than that pivot, or sorry, than that median, because obviously in this block right here, I guess you can't see the mouse, but in this block right over here, if we sorted them, then these two are going to be both smaller, and these two have to be both larger. So basically, these two elements are going to be definitely bigger. Let's see if we can see them. I'm going to try to move the mouse here. I can't really see the mouse, but anyway, these two elements are both going to be bigger. And in the blocks to the right of this element here in the space pen, the median of each, so this element right here, along with these elements that are both larger than that median, these must be bigger than that space pen highlighted median. And likewise over here, these elements have to be bigger because this median right here, you can't really see it due to the mouse or due to the dark theme here, but this median has to be bigger. So then therefore these two have to be also bigger. So hopefully this part makes sense, that these elements must be larger. Then likewise, all of these elements have to be smaller. So I guess the blue is smaller, so I'll kind of highlight this. So smaller, and the red will denote larger. Same idea, since those two medians of those lists are both smaller than that space pen median, then the elements that are the median and the smaller than the median, those have to all be smaller. So all these elements right here, this is going to be obviously smaller, and these two are smaller than this element right here. Therefore, these are all going to be smaller than that space median. And same idea for the rest of these blocks. So we definitely can conclude that this is going to be the case. This is going to be the bigger and smaller elements. Now, I'm going to, I guess I'll just highlight like this. I'll do the file. I'll just kind of do it like this. These elements right here, well, these are X factors. We don't know if they're really going to be bigger or smaller. We have no clue. We can't make any type of logical guess. We can guess, I suppose. We can't make a smart guess. We don't know about these guys. These are actually, so I'll just go ahead and I'll just put in here. These are going to be just kind of question marked, as we don't really know. essentially, whether it's bigger or smaller than that space pen circled the median among all the medians. So, alrighty. So let's suppose, now, of course, we can partition, and then that space pen selected medium happens to be the median of the entire list. Well then, if that's the case, we're done. But let's suppose, for right now, that this median of medians happens to be smaller than the true median of the list. Then that means that the element that's going to be the median has to be larger than this item. So let's go ahead and just write some stuff over here, so it might be better for notes. So suppose, I'll use like a dash here. So suppose after partitioning the list, the median of medians is smaller than the potential median, than the median of the list. Let's suppose. So then how many elements can we for sure eliminate? So how many elements can we eliminate? And of course, in the worst case, because we're only interested in the worst case. The worst case really encapsulates every potential possible case. So let me go ahead and just zoom out so we can see all of this. I guess it's not really, okay, it's good enough. So if, let's say, the median of medians is smaller than the true median, then all we can really do is just eliminate that blue these blue values can be eliminated only. So let me go ahead and just say, kind of informally, only the blue elements can be guaranteed to be eliminated. That's all we can do. So that means if the median is smaller than the actual median of the whole list, now obviously the red elements, the median could be somewhere here in the red elements. And these question marks will assume that in the worst case, they're both going to be larger than the median of medians. So therefore, only the blue elements can be eliminated, guaranteed. Now, in a better case scenario, maybe some of those elements in that zigzag line boxes, that question mark area, maybe those could be, smaller. So maybe those wouldn't be eliminated as well. But in the worst case, we don't know, so we assume in the worst case that those zigzagged areas will also be bigger than a median of medians. And red ones, of course, are also bigger, obviously. So only that blue region can be eliminated. Now let's go ahead and write the notes here for what about if it's smaller. Sorry, what if the median of medians is larger? So let me go ahead and I'm going to actually just sort of copy this to avoid writing all this out again. One of the benefits of using OneNote over an actual in-class board. So I'll erase this part here, just because. Suppose after positioning the list, the median of medians is larger than the median. How many elements can we eliminate in the worst case? So in this case, only It's actually supposed to be blue elements. So only the red elements can be guaranteed to be eliminated. So if the median that we're looking, let's say we have the median of medians, we partition the list, and then the median, the true median, has to be on the left side of the median of medians, chosen as your pivot. Then the elements that are larger than the pivot, well, those will definitely all have to appear on the right side of the pivot chosen, median of medians. After you swap that with index j, then the red elements are guaranteed to be on the right side. On the left side, however, well, of course, the blue elements will be on the left side, and then these question mark regions, well, we don't know, so in the worst case, they will also appear on the left side. So no matter what we do, if let's say we partition the list and the median is smaller, these elements that are on these red elements for sure will be on the right side, and we'll assume in the worst case these squiggly line regions will also be on the right side. So only the blue elements are eliminated in that case. Likewise, if let's say we partition this list and the median of medians, this space pen highlighted median element, is actually larger than the potential median of the list, then we know for sure the blue elements will definitely appear on the left side, and the right side will appear these elements. So on the left side, the blue elements for sure will be there, and these question mark regions, we'll assume in the worst case, are also going to be there. So that means in the worst case, we can only eliminate either just the blue elements or the red elements, and that's it. Now, in a better scenario, in a more average case, it's not going to always be that. But in the worst case, though, you only can eliminate that many elements. So let's go ahead and figure out, well, how much is that? So how many elements are in the blue or red region? Let's go ahead and just sort of go back and forth in our notes here. Actually, I will not zoom out. I'll just keep it the same way as it was. I won't zoom out. So I can go back and forth. So then, how many elements will appear, how many elements are in the blue or red regions? So looking at this picture, so how many columns do we have? Well, we have n over 5 columns. And looks like we're breaking this in half, sort of, in a way, right? Because we have the blue half and the red half without these guys. So we have really n over 5 divided by 10. I'm sorry, divided by 2. Because we're going to sort of break this in half, basically. So we have half the number of regions on one side, half on the other. So we have this left half. So left half will be everything to the left of the that space pen highlighted median. And we have the right half. So we have n over 5 divided by 2. So we have basically n over 5 multiplied by 1/2. And going back up once again, in each region, whether it's the blue or us, whichever region gets eliminated, whether it's the blue or red, we're going to have 3 elements in each region that's going to get removed. Because really we can think of it as, well, we're going to eliminate the median of medians as well. This is going to get also, we're not going to, this gets eliminated as well, essentially. No matter whether we pick the left or right side, this gets eliminated. So, which means that we're going to have 3 elements in each block that gets eliminated. So it's always going to be 3. These, or likewise, if I were to the other way around, same argument, you would sort of, it's always going to be 3 in each block. So basically what that means is we're going to have 3 in each block that's eliminated. So we're going to have 3n over 10 elements eliminated. So in the worst case, only 30% will get eliminated after every single step for this selection problem, because we can only eliminate just the blue or red sort of regions. So it's going to be n over 5 total divided by 2, because we're now going to split this in half, and then multiply it by 3 because there's 3 elements per region that's going to be eliminated. Because of n over 5, and we sort of cut that in half, it's n over 10, and these n over 10 regions, we're going to have only 3 to be used that will be eliminated. Other ones, well, we can't eliminate the other ones. So we have this many. Wait, what happened to one note? Why is it all gone? Okay, there it is. That was weird. So that means, well, now we know how many elements we're going to always consider every single time. Now we can finally have a recurrence relation created. So T of n equals T of n over 5, because we're first going to break the list into n over 5 pieces, and potentially have to recursively keep on working on n over 5 pieces if, let's say, the number of medians is very large. And once we have our median of medians, we have to recursively call selection again, but pass in 7n over 10, because 70% of the elements will be considered now, because 30% are gone, 70% is left over. So you first break the list into n over 5 pieces and recursively keep on working if n over 5 is too much. After we find our median of medians, we partition the list, which takes theta of n time. And then we have to break the list, and 30% is eliminated, so 70% will be used. So this recurrence relation actually is going to be a selection problem. So you might have noticed this on, I think, the homework assignment. I had this recurrence there on purpose, because that means you worked this recurrence relation out already. So this one, I believe, ends up being around roughly 10n, if I can remember this correctly, which means that theta of n, or sorry, T of n equals theta of n. This recurrence relation, if we are in fact going to solve it, is theta of n. I believe it's 10n, but that's still n. So that means we can use this selection problem to find the median in linear time, and then we can recursively call quicksort on the 2 halves. This is if you use selection sort to break our list into these 2 pieces, and recursively call quicksort on both sides, we will sort the list guaranteed in n log n time. So the conclusion here, I'll just sort of, I think I wrote this too large. I'll have to like sort of fix this. Well, I guess I'll just keep doing this now. Well, I'll fix it later. So anyway, the result is if we use the selection algorithm to find the median, and of course the selection algorithm, it does break the list into 2 pieces, so it's going to so if we use the selection algorithm to find a median and break the list into 2 n over 2 pieces, and then call quicksort on each piece, then quicksort is guaranteed to run in theta and log n time. Because doing this selection takes a linear time. So in linear time, we will find the median, and also subsequently, it's going to also break the list into two pieces as well. So then we have the list broken into two pieces, we quicksort both sides, and we will get that linear runtime. Now, of course, if let's say we break the list into 30%, 70%, it'll still be linear, but breaking in half perfectly is going to still, it will not take more time to do that. So we get a nice runtime. So that'll be it for this sort of lecture. So I did spend almost 75 minutes, just like a real lecture. So anyway, that'll be it for right now. We'll have our normal class, you know, I'm not doing our normal class times this week. So I guess take care, you guys. Stay safe. Thanks for watching, and till next time.